Okay, so we'll finally, after day 3, finish up this big lab that we started. So when you look at that first question, and this is going to be important when you get into like your assignment for today. So you have 2 different equations for harmonic motion. One is a pendulum 2 pi times the square root of L over G. And the other one is the period of a spring, which is 2 pi M over K. Now, here's kind of what you want to look at. What's a factor and what's not a factor? So no matter what, whether it's a pendulum swinging like this, okay, or a harmonic oscillation like that, here's what they have in common. In both situations, when they're at the top or bottom or the end of the swings, it's going to be some form of kinetic energy. And that kinetic energy is going to be 0 on the ends, whether you're an oscillating thing going back and forth or a pendulum like this, because you're going to stop and you're going to change direction. When you're at the middle, that's when you're having your maximum velocity, no matter what, okay? Because this thing is going to speed up, hit the bottom, boom, start to slow back down again. And the same thing is going to be true of an oscillating mass. It's going to start at some velocity of 0, it's going to speed up, hit the middle, boom, begin to slow down. You're going to have us, okay, in the spring. You're obviously not going to have any us because there's no springs involved in this one. But you're going to have UG there as long as it's oscillating vertically. The other thing that can happen is that we talked about yesterday with springs. Springs can oscillate horizontally as well. And that actually makes it a little bit easier to view, because if you're oscillating horizontally, you only have to worry about potential energy stored in the spring, and you don't have to worry about the gravitational acceleration. But obviously pendulums only work in a gravitational field. If I'm in the space station and I try and do this, it's just going to keep going around and around and around and around like this, because there's no gravitational potential energy. The other thing that's common to both of these is that notice on both of these, amplitude is not a factor, okay? Amplitude isn't there. So when you look at the period of this pendulum, whether it's like this or whether it's like this, period is going to stay the same because it's not a factor. The same thing is true of an oscillating spring. Whether I have it like this or I have it like that, doesn't make any difference. It's still going to have the same period as long as it's still the same spring, as long as everything stays the same. So you have to look at what's a factor. Now, what's different is that this, on a period of a spring, is impacted by the mass of what's oscillating, okay? That's a factor. Bigger the mass, bigger the period. But on a pendulum, the mass of what's on the end of the string, otherwise known as the bob, isn't a factor. So if I double the mass of the bob on the end of the pendulum, doesn't change anything because it's not a factor. I double the mass on a harmonic oscillator, that's going to increase the period, okay? Now the other side of it is that my gravitational acceleration is a factor on a pendulum, but it's not a factor on a harmonic motion problem with the spring. So they both involve 2 pi, and the reason that they both involve 2 pi is because, and this is what we talked about. So imagine that I'm swinging this thing around over my head, okay? And if you look down on top, you could look and go, oh, that's traveling in a circle. Oh, well, in a circle, 1 revolution is 2 pi radians, okay? So if this thing is going around over my head, you have 2 different perspectives. If Vitor is looking down on top, he's going to see this thing going around in a circle. He's going to go, oh, Mr. Burkamp, 1 revolution. It's cool, right? You travel through 2 pi radians. Now, if Gracie is sitting here and all she can see is the horizontal motion, Okay, she has no depth of perception. The only thing she can see is the horizontal. What Gracie's going to see is she's going to see this thing going back and forth like this. Okay? She can't tell that it's going around in a circle. So for Gracie, whether I just hold it in my hand and go back and forth like this, she can't tell the difference. If it's going back and forth like this, or if it's going around in a circle, because that's all she can see. So this is why in one revolution there's 2 pi radians. This is why 2 pi is a factor, because of the fact that even with this, as this thing goes around like this, okay, you can view it as traveling through part of a circle. Oh, there's 2 pi radians in a circle. That's where that 2 pi comes into play for both of these. Okay, now, so when you get to this first question, and it's got lightweight L, da 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 da, okay? Now a body of mass 4m. So on that question, they tell you to increase the mass of 4m. Does that make any difference at all in this calculation? No. Completely misguided. Okay, they didn't, at that point you should go, that doesn't matter. Okay? Doesn't. Now, does it affect the potential energy of the spring? Yeah. Okay, it affects that, but it doesn't affect that calculation. So as you go through this, one of the most important things you've got to be able to do is to discern what's a factor and what's not a factor. Now, in this one, you're talking about frequency. So here's the deal. So, and this is you're going to use the same technique. So I'm just going to start with this one because we're talking about a pendulum times the square root of L over G. So if you talk about frequency, then it's the inverse of this whole thing. So this becomes 1 over 2 pi times the square root of G over L. Now, here's why you have to take the inverse of what's underneath the radical. If nothing else, look at the units. Oh, G, literally. That's meters per second squared. Length of the pendulum, not angular momentum, Louis. Meters, right? Meters cancel out. You're taking the square root of 1 over second squared, which is 1 over seconds. That's frequency. Okay, so this is why you have to flip what's underneath the radical to make the units work out. So if it's period, it's this. If it's frequency, it's 1 over 2 pi. You're basically taking the inverse of the whole thing. Okay? Now, there's a couple of ways you can handle number 1. I don't care. Option number 1 is that you just make up numbers. You go, okay, here's my frequency. You know G is 9.8 meters per second squared. Maybe you want the length to be 1 meter. Cool. Okay? So you could go through and you could actually numerically calculate that frequency. You could. You could get a number. Then it says, now Bob mass 4 is, and we're going to increase the length to 4L. So one option, and again, I don't care how you do this. So one option is you can sit here and go, okay, 1 over 2 pi, that was horrible, 1 over 2 pi, times the square root of G divided by 1 meter, and you could calculate that frequency. Cool. Then, to find the new frequency, you could go 1 over 2 pi times the square root of G over 4. And you could get that value. Now, here's the problem. With this one, you could probably still see the relationship. But if it gets weird where you have like square root of 1/2 or radicals, then it gets a little sketchy. This works, but because you're just comparing numeric answers, it's more difficult to kind of see, hey, what's actually taking place. If you go with the smash mouth physics, it works, you get numbers, but it's hard to make the comparison. Now, if you go with a more elegant approach, and the sooner you embrace this idea, the better off you're going to be. So the more elegant approach is to go, okay, 1 over 2 pi, G over L. That's my initial frequency. I don't know what the length is. I don't care what the length is. It doesn't matter. It's just G over L. That's it. Now, my new frequency...
Isn't it L over G?
Well, no, it's the inverse.
It's the inverse, so it's G over L. So that's going to be 1 over 2 pi times G over 4L. Okay? Because that's what you've done. You've increased the length. Now, let's just think this through. Let's just think this through. So here's a pendulum like this. Okay? Has a certain frequency. So visualize what that frequency is with this. Now, I'm going to make it really, really, really long. Okay? Increase that length. So what's happened to the frequency? Has it gone down? Right? You won't see this going by as many times as if I have something like this. Okay? So I know my answer has to be less than the original one. So right away, I know it can't be D or E. Can't happen. The other way that you can look at it and eliminate those is, look, you're dividing by L. So once you divide by L, if you divide by a bigger number, what's going to happen to your frequency? It's going to become small. So right away, I've eliminated D and E because I'm dividing by L. Okay? Now, if you go with this approach, this is where kind of the mathematics kick in. Can I write this as 1 over 2 pi times the square root of 1 over 4 times the square root of G over L?
Yes.
Is that cool?
Yeah, that's cool.
Is that cool, right? Why is that cool?
Because it's
Pen
just
does.
separating the radicals.
Well, everything's underneath the radical.
Yeah.
Okay? That is, it's really not.
Just math rules.
Yeah. So here's the deal. What's the square root of 1/4? 1/2. So this becomes 1/2 times 1 over 2 pi times the square root of G over L. Okay? So basically what's happening is that I'm taking half of what was my original frequency. Since I'm taking half of my original frequency, the correct answer for number 1 is B. Yeah, B. And again, you can either do the smash mouth physics or you could go with a more elegant approach. Okay, in this situation, and it's always going to be true, the more elegant approach actually saves you hassle because then you don't have to go through and like crunch up numbers and everything else. Okay, it just allows you to see a more pure form of that relationship. And then now let's talk about number 2. So on number 2, you've got if the speed of the mass is past equilibrium is 10 centimeters, what's the amplitude of the mass oscillation? So when you look at this concept of the total energy that can exist, okay, that total energy is going to be the sum of us and KT, and then I'm going to put us and KT over here. So if you're at the amplitude, okay, in other words, you're as far away from center as you can possibly go. You are at your maximum amplitude. What's going to be the value of your kinetic energy? 0. So my us, because of the fact that you're talking about a spring, not a pendulum, talking about a spring. So I'm going to write that as 1/2 K, and instead of x squared, this only works on the extremes, okay? This only works on the extremes. I'm going to put that as 1/2 K A squared, okay? It's the same equation for the energy of a spring. Instead of 1/2 kx squared, I'm going to put 1/2 ka squared. But listen to me, listen to me, listen to me, listen to me, listen to me. That only works when you're at the extremes of the oscillation. If you're at any point in between, can't do that. Okay? Cannot do that. Now, when you're at the midpoint, okay? So this thing is oscillating horizontally. When you're at the midpoint, what's your amplitude going to be? 0. Guess what? How much S are you going to store at the midpoint? None. Guess what? All that energy exists as kinetic. So this becomes 1/2 mv squared. Halves cancel out. Boom, you're off to the races. Okay? When you get to number 3, okay? So what's going to happen on the difference between 1 and 3? 1 is a pendulum. 3 is a spring. But it's the exact same idea. Okay? It's the exact same idea. So go through, see what's underneath the radical. Okay? So let me give you a hint. Okay? Look at what's happening underneath the radical. When you get to question number 4, there are 2 springs. Okay? There are 2 springs. Okay? So that means that basically means that each one is supporting like half the weight. So because it's a spring, and this is going to play out large later on, you have F equals kx. Now, as long as you're allowing gravity to do the work to provide the force, you could write that as mg. Okay? Fundamentally, that's what it is. Okay? It's mg. Because as long as gravity is pulling it down, that force, you can just write it as mg. Then you have k, and then your x is going to be your elongation. Sometimes you'll see that written as delta L. Okay? So this is a different way to write that same thing. Okay. So basically this is going to make a linear graph like this. There you go. All the other ones are fairly straightforward in terms of that concept. When you get to that last question, on question number 8, you have to pay attention to how they're defining the system in terms of positive amplitude or negative amplitude and where it's starting. And then make sure your position time graph matches up with your velocity time graph, when it's speeding up and when it's slowing down. Okay, any questions you want me to go over on the multiple choice? Okay, so here's what I want. Basically, hand this in sequence. So you're going to have the first page from day 1. Then you're going to have the yellow page, then the blue pages, and then the graph for the scale. Okay? So it's just basically the sequence that I gave that out to you. And then staple it all together, hand it in.
You want me just to turn in my blue one?
Huh?
You want me to just turn in my blue one or just wait?
Just wait and hand it all in. 'Cause I'm grading it as one big lab.
Okay.
Yeah.
What?
Graph too.
Huh?
Did you already say that? You want the graph
Staple the graph to the back.
to the back? Okay. Thank you.
What?
I have a feeling this is, or I know it's wrong, but I just don't know why it's wrong. This is where my mind went on this equation. I used, or tried to use energy anyways.
No. Look, don't. It's just linear. It's just.
Well,
Don't.
yes.
Get over the energy thing. Okay?
I want to use energy.
Don't. You don't have enough information to calculate the energy.
Yeah, what?
Do you like that one?
Just use F equals K.
Okay,
Gravitational pull is here,
yeah.
but each spring is carrying half the load. So it's like you're going to have a graph, right?
Yeah.
You're going to have force here, and you're going to have elongation here,
This Kim, this Clay.
and
Excited,
There you go.
man.
Don't start down there.
Just telling
It's
the
just
story
gonna-
about the
Inception.
text or whatever.
Okay.
I was like, oh.
She's so nice.
She's so funny.
Hold on, let me do a little drawing here.
What you said, what do about her eating a passion?
No.
No? She's done it before.
I should actually.
It was a cat or a dog, I forgot which one.
So has it,
Neil laughing.
you're being 100% serious right now?
That I know it usually has a dog.
Yeah.
Yeah.
Riley, you have, right?
No, I haven't personally.
Oh, never mind. I'm just tripping, man. That's crazy.
What kind of dog was it?
Just anything off the street.
Did you get like a picture? Did you get like a picture of it? You're joking, right?
Yeah, I'm joking.
Uh,
No, I'm just kidding. I'm not joking.
I'm just kidding about joking.
Yeah, nice. I'm joking.
Don't worry,
Your
guys.
mom's eating.
Which one?
I don't even.
Oh, yeah.
Damn, there's so much eraser.
Yeah, me too. Sorry. Oops.
So today we're gonna have we're gonna try out some random loose ends. And we don't really have time to start like a whole new thing. So we're gonna try out some loose ends and you'll have, for this class anyway, a relatively large amount of time to work on your assignment for tomorrow. So, or finish up the lab if you need to do that. Okay. So I'm basically today going to show you through some of the hocus pocus on how these functions work and tie together some different things. So on your book on page 444, you have this function equation. So what you'll see is you're going to have three different equations. One's for position, one's for velocity, one's for acceleration. On the test, which is going to be Friday, right? If you need any of these obscure equations, I will give them to you, okay? I'm not going to expect you to memorize them, so if you need any of these weird equations, I will give them to you. Don't memorize them. You just have to know how to use them. So, what we're going to look at is how harmonic motion, and we're delve a little bit deeper into this, ties in with circular motion, okay? And again, it's kind of all a matter of perspective. So what's in your book is this function equation for where an object is at time t. So here's how I can tell that I've got to be working with position. Because the only thing on here that has any units at all is amplitude. Oh, okay. Well, amplitude is your position. It's a fancy word for that. Okay. Well, that has to be measured in meters. Okay. Because the cosine 2 pi t over t, that doesn't have any units. So right away when I see this, I know, oh, this has to be keeping track of position as a function of time. Because that's the only thing that has any units to it. So one of the key substitutions, and this is what we've talked about, is that period and frequency are inverses of each other. So either period equals 1 over frequency or frequency equals 1 over t. So all I did was that because period equals 1 over frequency, I took that and substituted that in here for period. Okay? All I did was that simple substitution. So this is 1 over frequency. So then that's the denominator of the denominator. The frequency flips up. You get this. So this equation here is the exact same as that equation there. You're like, ah, really? Yeah, it's the exact same thing. Because look what happens with units. So when you look at this, so you have seconds here and seconds. So if you look at this, you have seconds divided by seconds. The seconds cancel out. You don't have any units in terms of that. Here you have seconds multiplied by frequency. Frequency is 1 over seconds. Again, the seconds cancel out. So you're taking 2 pi time, or cosine of 2 pi times some value that doesn't have any units. Okay? Same idea. So what will happen here is that because this is the function equation, typically what's going to happen is that they're going to give you the frequency, they're going to give you the amplitude, and then you're going to be asked to keep track of where the object is as a function of time. They're going to say, oh, t is 0, time is 1/4 t, time is something, okay? So when you're doing this, just make sure that you're in radian mode. Now, this is where it ties in with circular motion. So here's the other side of the coin. So when something's moving in a circle, remember omega is going to be in radians per second. So if I take this wheel, right, give it a spin. So if you're looking at, imagine that I've got like a beaker, and it's sitting here, and it's going to go around like this. If that's what's happening, you're going to see that beaker go back and forth if that's all you can see. You're going to see it start here, go there, and you can't tell if it goes here, here, and back, or if it just goes all the way around, if all you can see is that motion. So when you look at this omega, okay, remember omega is radians per second. So one way that you can calculate omega is if I said, hey, let's calculate the angular velocity of this wheel. So one option is that you say, okay, it's going to travel through 1 revolution. Okay, that's cool. It's going to travel through 1 revolution. Oh, 1 revolution is 2 pi radians. Oh, okay. So up at the top, I've got 2 pi radians. That's all it is. So don't flip out and go, oh, where does that 2 pi come from? It's 1 revolution. Okay? Then I'm going to divide by t. Oh, that's how long it took. Oh, I get radians per second. So clearly, if this thing is going pretty slowly, I'm going to have a relatively small number of radians per second. If it's going a lot faster, then I'm going to travel through a lot more radians per second. Now, here's where this is where this all kind of turns into one big picture. So here I've got 2 pi over t. I took this is 1 revolution. All I'm saying is that this is 1 revolution divided by how long it took for it to make that revolution. That's all I did. Now, if you come in here and you say, well, period is 1 over frequency. So if I come in here and substitute 1 over frequency here for period, that frequency flips up and I get 2 pi f. So 2 pi f is the same as 2 pi over t. It's the exact same thing. It just depends upon if you're given frequency or if you're given period. That's the only thing that you determine which one you've got. So since this is 2 pi f, and that's what omega is, so here's the big substitution. Okay, so here's the big one. So omega can equal 2 pi f. So I can take 2 pi f and substitute this 2 pi f for this omega. So you can also see this written as a cosine omega t. So here's what I want you to see. Even though they look completely different, all 3 of these equations are fundamentally the same. Okay? It just depends upon what you're given in the problem. If you're told that this thing is oscillating through, 4 pi radians per second, cool. And you want to find out where it is at a particular time, use that one. If you're given frequency, use that one. If you're given period, use the top one. Okay? But they're all 3 the exact same equation. It just depends upon what you're given in the problem. Okay? So don't flip out when you go, oh man, we've never seen that one before. Sure you have. It's just a substitution. Okay. So there's that. So when we talked about us, okay, so now we're going to be back to oscillating springs. Okay, it's all going to be random because of all. Like I said, I just need to tie up some loose ends. So us is going to be 1/2 kx squared, and then you can have kt, which is going to be 1/2 m v max squared. Okay, so if you look at the extremes, okay? If you look at the extremes, if something's fully expanded, you can write that as 1/2 k a squared. If it's in the middle of the oscillation, you can write that as 1/2 m v max squared. So what that means, because energy has to be conserved, if you know one or the other, you can solve. So here's the deal. So what I can do is, because the energy at the extremes has to equal the kinetic energy in the middle. So I can set this equal to each other and go, oh, that's 1/2 m v max squared equals 1/2 k a squared. Okay, well that's kind of cool. So the 1/2s cancel out, those go away, okay, because that's on both sides. So if I solve this for v max, and you can solve it for anything, I just chose v max. So that's the square root of ka squared over m. Now, but what's the square root of a squared? A. So you can also write this as a times the square root of k over m. Okay? So again, this is one of those deals where you set them equal to the extremes. Okay, right. Look at that, but think this through. If I don't have any amplitude, what's my V max going to be? If I have no amplitude,
Oh, it's gonna be 0.
0. Guess what? I don't have a V max because it's not moving because I don't have any amplitude. Now, if I have just a little bit of amplitude, what do you think is going to happen to my V max? Pretty big, pretty small? Pretty small. If I go big, okay, and I have a bigger amplitude, what's going to happen to my V max? It's going to double. Now, here's an interesting thing. So the relationship between amplitude and V max is a straight linear relationship. If I double my amplitude, I double my V max. But think this through all the way to the end. If I double my amplitude, what impact is that going to have in terms of my maximum kinetic energy?
Oh, it's gonna quadruple it, yeah.
It's going to quadruple it. Why, Louis?
What?
If I double my amplitude, why will that quadruple my kinetic energy in the middle?
Because mv squared.
Yeah. So if I double my amplitude, I double my V max, right? And my kinetic energy is 1/2 mv squared. True? So if I double my amplitude, I double my velocity. If I double my velocity, I'm going to increase my kinetic energy by a factor of 4. Okay? Cool with that. Now, if I double my amplitude, what's that going to do to the potential energy in the system? It'll also quadruple it. Why?
Because the amplitude is squared too.
Yeah, because it's 1/2 ka squared. Okay? So here's the point. As that thing begins to oscillate, I can't say, oh, if I double my amplitude, my us is going to go up by a factor of 4, but my kinetic energy is only going to go up by a factor of 2. Okay? I can't have, because the sum of these always has to equal a constant, I can't have one value being quadrupled and the other value just being doubled. Okay? But that's what I want you to see. How do these things all fit together? Okay. Now, speaking of which, we said frequency equals 1 over 2 pi times the square root of k over m. Pendulum or a spring? Spring. Why? Okay? There's no length. There's no gravitational acceleration, right? So now I want to multiply this by 2 pi. I'm going to get 2 pi f equals the square root of k over m. True? Now, what did we say 2 pi f equaled?
A.
Well,
Oh wait, no, angular momentum.
omega, right?
Yeah.
So could I write this as omega equaling the square root of K over M. Valid?
Yes.
Okay?
Valid.
So if I square both sides, I get butt squared equals K over M. So K equals M butt squared. Okay? So what that means is that this is another way to calculate K. So when you look at how you can calculate K, you could set up a graph and you can have force and elongation. You can have F equals Kx. That's one option. Okay? That's one option. You could go period equals 2 pi times the square root of M over K. So you make that spring oscillate, you measure the period, solve for, and you know the mass is on the end of it, you can calculate K that way. You could use, if you know the frequency, you could get K that way. The other option is that if you know radians per second, and this is realistically, mathematically, it's the coolest, but this is the most difficult to physically measure, because this one's simple, okay? You did that the very first lab you were in here. Oh, I'll hang a 1 kilogram mass, I'll measure how far it stretches, okay? So this is the simplest because there's no moving parts to it, okay? Oh, there you go. How much mass does it take? Oh, that's cool, right? So then this one isn't bad, but again, you've got to measure things because now you have to measure time, right? But still not bad. This one's a little sketchier because then you have to worry about frequency, so then you got to count. It's like, oh, how many cycles per second does it make? And that's a little sketchier, okay? This one would actually be the hardest to physically measure because you'd have to measure radians per second to actually have that. So when this thing is like oscillating, it's like, well, that's a cool idea, but how do you get radians per second out of an oscillating spring? So there's 4 different ways you can get K. One's pretty easy to measure. The other one's, the period, you did that one, not bad. Frequency, that's a little sketchier. This works, but tough to do. Okay? Got that. All right.
Who's skiing? Yeah, he'll be back tomorrow.
You went skiing in the middle of the week?
Yeah, rude.
Monday and
Well, I'm
Tuesday.
sure he went during the weekend. And
No, he was here Monday. Wait, was he?
No.
No.
Oh.
Is that a T?
Yeah.
Which
It's probably
one?
like
I mean, like
Saturday.
in the 2 pi F
Three-day weekend
A
next
T?
week. Why did they choose?
No, that's the one you got.
Like
There's
a
probably
cap.
less people on the slow.
Just say.
Yeah.
Everybody has to
The
do-
really long.
Oh, I guess
It's
it's
in, not everybody's.
I think you're lying.
Vmax equals 2 by FA? That's what you're talking about?
Is that an A?
Yeah, it's
There's
an
no T in there.
Oh. Where'd the T come from?
Okay. So here's another set of random equations that all look completely different, but they mean the same thing. So if you look at another way to calculate Vmax, okay? So the simplest is 2 pi over period times your amplitude. So if you look at calculating that Vmax, so as that thing oscillates back and forth, what would be simple to measure is the amplitude. Oh, measure how far it moves off that equilibrium position. There you go. Measure the period. How long does it take to oscillate back and forth? Boom, there's your Vmax. So that's physically the easiest way to measure your maximum velocity on an oscillating spring. But if you look at what the units are, notice that they all involve an amplitude. It's going to be in meters. And then they all end up with 1 over seconds. Because here you have 2 pi over t, so you have meters over seconds. If you have 2 pi FA, that's frequency, which is 1 over seconds times amplitude. You have radians per second, radians float out, so then you still end up in meters per second. So even though these three equations, again, look vastly different, they all at the end of the day are meters per second because they all involve amplitude. Now, what's common to all of them, again, if you double the amplitude, what's that going to do to your Vmax?
It's gonna quadruple.
No.
Double the
It'll
max.
double the Vmax, but it'll quadruple your
Energy.
energy. Okay,
That's what I meant.
now, last problem. So we're going to have an oscillating spring, okay? And it can go back and forth like this with some amount of amplitude, okay? Maybe make that negative, maybe make that positive. Here you are at equilibrium, okay? So when the displacement is 1/2 the amplitude, okay? So in other words, let's say the amplitude is, I don't know, 0.10 meters. When it is at half of that, which is 0.05, okay, half that, what I want to know is what fraction of it is kinetic energy and what fraction of it is potential energy. So I'm at half my amplitude. So I want to figure what fraction is your potential and what fraction of it is kinetic. So, do you think it's just going to be 50-50? Here we go.
No.
Why not?
Because it's
Vitor.
not
Because it's-
easy.
Because the A is squared.
Ah, because A is squared.
Is it a 3/4 1/4?
Yes.
Could be.
2/3.
But which one is which?
The K is one, or the kinetic energy is 3/4.
Why?
Because A is squared. So
So what?
if you square 1/2, you get
A
1/4.
squared, bro.
So it's like
Because you're keeping everything else, or you're keeping
because
keeping
1/2
the-
is squared.
other part constant.
Okay, let's look at this, right? If I just ask you to calculate the potential energy, okay, you would start with 1/2 kx squared, right? That's what you would start with, 1/2 kx squared. Now, this does go back to something that Vitor said. So in this situation, I can't use A because it isn't fully elongated.
No.
It's half, right?
Oh, you can do A minus.
So I'm going to have 1/2 k times,
A minus.
1/2
well, just,
A.
how about just amplitude over 2 squared?
Oh, yo.
Oh, yo!
That's dope.
Oh, yo. Okay. So,
Isn't that the same as in
Xbox recorder.
Mom, get the camera.
Crazy.
is that cool with what I just did? A squared over 4?
Yeah, I like that.
Okay. So could I write that then as 1/4? I'm going to pull out, like, in effect, that 1/4 and have 1/4 of 1/2 Ka squared.
Yeah,
You can do that.
Can I do that? Is that cool?
that's. Yeah.
So 1/2 Ka squared gives me my total energy, right? So this means that at this point, it's exactly what you said. 1/4 of my energy is going to be U. The rest of it has to be kinetic. So I'm going to have 1/4 U, and I'm going to have 3/4 K. Now,
Go to the back.
no.
I thought that's what he was doing too.
Yeah. What is that?
Where
Yeah, I'm confused.
is the energy
Going?
half and half?
Oh.
I have no idea.
Square root 1 over the square root. Is that?
What?
When A is.
No, he's
when
onto
A
something.
is.
Oh, he's onto something.
It's A over square root 2.
Yeah.
Why?
Because once you
Then
square it,
square.
then it's just multiplying it by 1/2 instead of 1/4.
Okay. So you want 1/2 U, right? Which is going to be 1/2 of your total energy, right?
Yeah.
True? And one way that you can express your total energy is 1/2 Ka squared. True? Because if you're at the extreme, it's all about you. Okay, it's kind of a freshman way to look at this. It's all about you. It's going to be 1/2 Ka squared. True? So, in this situation, if I take 1/2 times 1/2, I get Ka squared, right? Now, here's where this gets a little bit dodgy, okay? This U value here is going to be 1/2 K x squared, right? Because that's just generic, that's just a standard definition of how you calculate U. It's just going to be 1/2 kx squared. So 1/2 kx squared has to equal 1/4 Ka squared in terms of the amplitude, right? So what that means is I can cancel out those K's, and I'll multiply by 2, so I get x squared, and I'll multiply this side by 2, so this becomes 1/2. So to get x by itself, then I get a squared over 2, which is the 1 over the square root of 2 times a. So that's where that square root came from. So well done. Well done. Okay, I am done. Yeah, I'm done, but you have the rest of the time to work on the homework.
What's the homework?
But it's going to take you a while.
Just do radicals and main functions. Didn't you say?
Today, tomorrow.
Calculate the radicals.
Thursday, the test Friday.
No.
He said the homework.
You have 30 minutes.
You said we have.
Is the homework long?
Yeah.
Really?
So we have to do all the homework.
It looks, let me put it this way, it looks more daunting than what it actually is. I know.
I'm gonna take pictures of my book.
What? I have a book, I just don't keep it on me. I don't
I'm always stressed.
I don't do that. I was caught lacking in class.
I'm stressed with the book.
Oh, you're Oh, it's just the book.
Yeah, it's just the book.
That's it, right? Please, you stop.
Right?
I've just given you a hint on number 3.
Oh, that's it? Oh, I shouldn't have said anything.
That's it?
I was going to quit until you asked that question.
Are you serious?
No.
Sorry, man. How? 22. This is a very daunting assignment.
Daunting? It doesn't, it might be the. Yeah, I think
Okay.
It's not, okay.
Okay, Berg.
That's enough slices.
Okay.
That's enough slices.
Okay, man. Whoa.
Brother, man. What is this non-tom?
No.
Now I'm done.
Slice. Page
And again, answers on the left, work on the right, okay, in case you might have forgotten.
One significant digit.
Yeah, I just got a new picture of Berg. Berg, smile.
You're gonna have control.
Let's look at this slide. Okay, you shut up.
Let me give you a hint. Pay attention to what's a factor,
Yeah.
pay attention to what's underneath the radical, okay? What?
Look, it's a great picture. It's a great picture.
Myself.
Opt out. I had nothing to do
You have
with
to
it.
work 6 hours.